Now we're going to take a look at what happens when we have significant numbers of duplicate keys, which is not at all unusual in practical applications. So in fact, often the purpose of a sort is to bring items with equal keys together. Like the example that I gave where we had cities and times. There's a lot of detailed data in the times, but maybe the whole goal of the sort is to group them by cities so we can ship out the data for each city to each city. And there's plenty of other examples like that in data processing where we find maybe remove duplicates from a mailing list or all the job applicants that we get, we might want to sort them by the college attended. So the sort, there's huge files with huge numbers of duplicate keys. So our sort, it's worthwhile to take a careful look at what the implication of that is. So again, typical characteristics, we have a huge file, but small number of different key values. So let's look at our algorithms in that situation. So merge sort, it doesn't matter that much what the key values are like. Actually, we can show that merge sort always uses between 1/2 n log n and n log n compares. Quicksort, actually they were, up until the 1990s, the most widely used implementation took quadratic time for files with large numbers of equal keys. And it was actually found by an applications user. And that's the standard quicksort that was in all the textbooks, almost all the textbooks. If you did not stop the partitioning on equal keys, it would run in quadratic time. So we want to do better than this. So the mistake happens if we put all the items equal to the partitioning item on one side, which is a natural way to implement it. And the consequence is, if you have all the keys equal, then partitioning doesn't really do anything. It just peels off one key to do a file of size n, then you get a subfile of size n-1, and then n-2, and so forth. And the result is a quadratic time algorithm. Our implementation, we stop the partitioning scans on items equal to the partitioning item, and then in that case, when all the keys are equal, it's going to divide it exactly in the middle. And then in that case, you get n log n compares. But actually, when you think about it, why don't we just put all the items equal to the partitioning item in place? That's really a desirable way to look at it, and let's take a look at that option. So the goal is so-called three-way partitioning. So what we want to do is get the array into 3 parts so that now we have 2 pointers into the middle. One that is the boundary between the keys that are less than the partitioning element and those that are equal to the partitioning element. Another one that's the boundary between the keys that are equal to the partitioning elements and the one that's greater. And then in the middle are all the equal keys. That's what we'd like to arrange. Now, until the 1990s, conventional wisdom among people implementing systems was that it wasn't worth doing this. But actually, it's a problem that Edsger Dijkstra had proposed in the 70s as an example of a programming problem. He was really interested in analyzing correctness of programs and showing that how you could convince yourself that this program was operating as expected. But in the 1990s, we figured out that really this was going to be an effective way to sort. And this was taking a look at the Quicksort that a user found was broken. And now this method is incorporated into plenty of system sorts. So let's take a look at how it works with the demo. It's more complicated than standard quicksort partitioning. A bit more complicated because there's more to do. So now we have our I pointer, which is right to the left of stuff we haven't seen yet. And then we have 2 other pointers that maintain these boundaries. Everything to the right of GT is known to be greater than the partitioning element. Everything to the left of LT is known to be less, and between LT and I is known to be equal. And all the method does is maintain this invariant. So let's just do an example or two and see how that works. So we increment I and then figure out what to do. So now it's less than the partitioning element. So what we want to do is increment LT. So now we have one that's definitely less than the partitioning element, and LT is pointing at the partitioning element. And so now increment both LT and I. So that's the first case there. So now we have a second item, B. That's less than the partitioning element. So we exchange it with LT and increment them both. So we're moving the smaller ones than the partitioning element to the left of LT and keeping LT pointing on the partitioning element. Now what about when we get one that's greater than the partitioning element? So in that case, we exchange the one over at the right with I and decrement GT. So now we have one over to the right that we know is greater than the partitioning element. Notice that we didn't increment I because that element Z that was over on the right really hasn't been compared with the partitioning element yet. But we did decrement GT, so we made progress. So now what happens here? Now I is pointing to a bigger one, so we're going to exchange it with the one at GT and decrement GT again. And again, Y is bigger, so exchange it and decrement GT. Now we have the C. That one's smaller, so that's the first case. So we'll move it to the left of LT and increment both LT and I. W's a bigger one. That has to go over to the right. Now we have I pointing to an element that's equal to the partitioning element. And what are we supposed to do then? Well, to maintain the invariant there, we just need to increment I. And again, it's pointing at one that's equal to the partitioning element, increment I. And now one more time, and now it's pointing to one that's greater. So we exchange that with GT and decrement GT, and I's pointing to the one that was there, and that one's smaller. So we exchange it with LT and increment both I and LT. And now we're at a point where the pointers have crossed, I and GT have crossed. There's nothing that we haven't examined yet. So our partitioning is complete. Here's a trace of Dijkstra three-way partitioning for his problem, which is when there's just three different values in the file. Our problem, we were treating partitioning equal to the partitioning element as one value, less than as another, and greater than as another. And so this trace illustrates how we always make some progress, and eventually we get the file sorted. The implementation is amazingly simple. The whole partitioning process for three-way partitioning in the modern programming language like Java simply maintains the invariance as described in the demo. If we find one that's less, we exchange I and LT and increment them both. If it's greater, we exchange I and GT and decrement that. Otherwise, we increment I. Could hardly be simpler. In fact, is simpler in many ways than the standard implementation of Quicksort. In fact, there's an argument for just using this implementation of Quicksort and forgetting about HORS because it performs so well in so many practical situations. Here's a visual trace of three-way Quicksort for a situation with plenty of equal keys. And again, when there's lots of equal keys, then there's going to be a place where one of those is chosen as a partitioning element, and then a big chunk of the array gets handled just in the partitioning process. Now there's actually some deep reasons why this method is important. And one thing to do is to realize that the lower bound that we talked about before depended on the keys being distinct. The worst case for a lower bound is when the keys are all distinct. But if we have a situation where there are lots of equal keys, that model is wrong. It's not too difficult to get a similar lower bound for the model when we know that there are some equal keys. So, for example, this is a rather complicated formula, but not too bad. And it says that if you know that the ith key occurs xi times, you can write down a lower bound for the number of compares that are going to be required in the worst case. And what's interesting about three-way partitioning is that the number of compares that it uses is equal to this lower bound within a constant factor. So that's entropy optimal. What that means is whatever the distribution of equal keys in there, this thing is going to use a number of compares that's proportional to the best that you could possibly do. The proof of this fact is quite beyond the scope of this course, but it's still an important fact. And the bottom line is that if you randomize the order and use three-way partitioning, then there's a lot of applications where your sort routine is going to be linear, not n log n. So it'll be much faster than merge sort in other methods for really a broad class of applications. So taking a look at equal keys carefully is something that can lead us to very efficient quicksort implementations.